look at solution sets of inequalities. In what we've done so far is we've been solving equations, okay, like 5x equals 15. We divide both sides by 5 to isolate the x, so we get x equals 3. Now, when we found this one solution, of course, that makes this equation true, so 5 times 3 would give me 15, so that's my answer there. But we never graph these things because it's pretty uneventful when you graph them on a number line. All you get is the point 3 marked on a number line. What we're going to look at today is when you have an inequality up with multiple solutions, and so now it becomes more relevant to graph the solution set or the values of x that make it true. So when you graph these, what you want to do is start with your number of interest. This is kind of the break point for what x is. This is red. X is greater than 2. So we certainly are going to put that point on our line. So let's mark it 2. And then as far as other points, just make sure you give direction. So in this case, I've marked 0, 1, 2, 3, so we know that small is to the left and big is to the right. And that's how you do want to set up all your graphs. Now, because we want the x's that are greater than 2, we're going to put an open circle here. And here's the x's, 3, 4, 5, etc. These are the x values that are bigger than 2 and would make this inequality true. So any number over here, plug in 6, 6 is bigger than 2. So my solution set is this infinite group of numbers. Some rules that you want to keep in mind when we read inequalities, you should generally always read them from the point of view of x and say x is this. So this is red, x is greater than 2. And the one below it, if you read left to right, it says 2 is less than x. But I think it's important to read it from x's point of view to go x is greater than 2. And then when you read it from his point of view, from x's point of view, you could see these two inequalities are identical. X is greater than 2, x is greater than 2. So if you read always from x's point of view, it kind of helps standardize the situations. Also, though, if you always get your x on the left, that helps a ton. When the x is on the left of your inequality, the inequality itself will point in the direction that your line goes. So in this case, x is greater than -2. So my arrow is going to point to the right, just like the inequality does. If your x is not on the left, this rule does not work. Okay, but like here, if I was doing x is greater than 2, that would be at 2 and would go to the right. But this one, because the x is not on the left, the inequality doesn't help me. But get the x on the left, and then the inequality points in the direction of your solutions. And lastly, this closed or open circle. We use the closed circle whenever we have greater than or equal to. Just like I showed you how we graph a single point when it's an equation, equal equation. That's what that bar means. Show us when it does actually equal it as well. So we have to fill in that endpoint. Open circles are used when we don't have the equality. Examples, x is less than or equal to -2, so you want to mark -2 right away on your number line. You don't have to be real fancy with this, just a few numbers on each side of it. Put a circle at -2, that's our point of interest. Now we're going to fill this one in because of the equal sign. So there's where x is equal to -2. And there's where x is less than it. Again, our inequality points to the left, and that's the direction our arrow ends up pointing as well. Okay, but it also just makes logical sense. I want the x is less than -2, that's -3 and -4 and -5, etc. Here we have to actually solve for x. Just like we did with equations, we'll divide by 3, and x is greater than or equal to 5, and then we can graph this. We'll mark our 5, a 6, and a 4. I want to be equal to 5 or greater than him, so going in that direction. Now here comes the one catch with inequalities, and that has to do with when you're solving it, and it's two rules. Rule number one, let's combine them into a single rule. If you multiply or divide both sides by a negative number, yeah, probably not a good abbreviation for your day and age, of a negative number, um, then you must flip the inequality. Okay, so anytime you are the one who instigates multiplying or dividing by a negative, and so in this problem, just following along with that rule, to get this x alone, I'm going to have to, it's negative 3 times x, so I have to divide away the negative. So I'm going to divide away negative 3. So I'm divided by a negative, and this rule right here says you have got to flip this inequality. And then just do the math. So 15 divided by negative 3 is negative 5. So our solution set is all the x's that are less than negative 5. So I've marked my negative 5, then smaller numbers are to the left. I want to include negative 5 because it's less than or equal to, and those are all those solutions. So here I divided by a negative, I've got to flip that inequality. And I just want to show you that with numbers and why that is true. Everybody would agree that 6 is greater than 3 is a true statement. Well, if I divide both sides by the same number, I'm going to divide them both by 3. And when I do that, you'll notice I get 2 is greater than 1, also a true statement. So our math works just fine. Just like we do with equations, I can divide both by sides by the same number. But watch what happens when I do that with a negative number. So this time I'm going to have 6 is greater than 3 again. And I'm going to do the same thing to both sides, but this time the same thing I'm going to do is divide by a negative 3. And notice I get negative 2 and positive 1. And it no longer works to say that negative 2 is greater than negative 1. This is no longer a true statement. Negative 2 is not greater than negative 1. However, that's a quick fix. As long as I remember to always flip it when I divide by a negative, it will work out because now it is a true statement. So whenever you multiply or divide by a negative, flip that inequality to keep it true. Here's another one. I'm going to divide by negative 2 on both sides to solve it. It's negative 2 times x, so I get x is, and I divide it by a negative, so I flip my inequality, and then just do the math. Negative 16 divided by 2 is 8. So x is greater than 8, so we'll just mark our 8. We'll put a 9 to the right and a 7 to the left to indicate direction. Open circle, because it's not greater than or equal to, and to the right, where 9, 10, and 11 are. Okay, so that's writing inequality we want to cover, or graphing inequalities, is what's called interval notation. And interval notation is just a different way to explain what your solutions are. Okay, so graphically, there's my solutions, everything greater than 1. I could write it as an inequality. I could say, hey, x is greater than 1. Or I can use this interval notation that looks like this. X is, and then you use this little backward C with a line in it. It's kind of like a epsilon. And then you just put the interval it's in. In this case, it starts at 1 and it goes to the right forever. And to indicate it goes to the right, you just say infinity like that. So it starts at 1 that goes to infinity. Now, we also have to indicate whether we include 1 in our answer or not. But to do that, we put an open paren right here. And on the other end, infinity doesn't have an end to worry about, so we'll put a paren like this. And that just says x is a member of this range of numbers, everybody from 1 to infinity, not including the 1. Let's look at this interval notation. First thing is the parentheses mean don't include that end number. So when I was going bigger than 1, I didn't want to include the 1, so I put a soft parenthesis like this. I didn't use this hard bracket. If I wanted to include the 1, if you want to include that last number in the interval, then you have to use the hard bracket for it. And then when you write down your interval, always go left to right, low number to high number. To look at an interval we could write. So here we've got -4, and it goes to the left. So to the left is your low numbers, and it goes to -infinity to the left. It just keeps on going. Okay, and then to the right, it goes all the way up to -4. And then we go, well, we want to include the -4 because it's filled in. So that's going to be a hard bracket to say, hey, I want to include the -4. And infinities always get the soft bracket because you can't include the end of it. So there's what our x's belong to. X's are members of the interval -infinity all the way up to -4. Another one. Well, I didn't want that slide to give you just one more example here. And have it go from -2. Ooh, let's just get kind of fancy here. We haven't done anything like this yet since we're making one up. I have one that goes from -2 to 1. Now we won't get any of these quite yet, but we will in short order. Okay, and to indicate this interval notation, we just go x is, and on the low end we got -2, and on the high end we got 1. So it runs from -2 to 1. And then we just have to figure out, are they soft uh, parentheses or are they a hard bracket? The -2 we do not want to include, but the +1 we do want to include. So we end up looking like that. And that's it. You should be able to do the assignment now. That many times.